Welcome to a lesson with Dr. Powell. Let's take a look at um, how many terms we have to add up in a particular series so that our error, or how far we're off from the actual, is maybe less than, let's give a tolerance of like 0.01. So how many terms so we're within like that much accuracy of the actual sum? So we can actually figure out how many terms to add by using integration, by comparing things. So suppose, for instance, that we have a series like, let's suppose we have something like n is equal to, let's do 1 over n cubed. And maybe we start at 3 and we're going off to infinity. How many of these terms do we need to actually work with this? Well, let's think about what's happening. Now, we can add, and maybe we'll add up to a certain point. Maybe the last place that we add is some n. That's where we're stopping. And then we're going to start at n plus 1, or, and this is for what we're not going to add is going to be the sum going on this way. Now, the sum that's going on this way is a series itself, and it's bounded above by an integral where we go 1 back over to this n. So that n right here should be the n that we need to add up to. So that's how many terms we're going to be adding up to. Only in this particular case, notice that we're starting at 3. So we'll start at 3, and we're going to stop right there. Okay. So really the number of terms that we'll be adding, think about shifting this list down. So we're starting at 1. So it goes shift down 2 to start at 1. So really, whatever n we find here, shift it down 2. So that'll be the number of terms. So it'll count how many terms actually we're adding up here in that series for that partial sum. So let's try that. Okay, so let's go from n to infinity, and let's see what we're doing. 1 over x cubed dx. And we'd like this, well, and to ensure that our error is less than 0.01, this is more than what we have left to add. Why don't we just try to get this integral and force it to figure out what n should be so this integral is less than 0.01. That'll actually ensure, in turn, that this whole sum right here of what's left to add will be less than 0.01. So let's go ahead and integrate this. This is x to the negative 3, so integrated we'll have x to the negative 2 divided by negative 2. So that would be like negative 1 over 2 multiplied with a x squared here. Okay, on the bottom. All right, so and that's from n off to infinity. Well, as x goes to infinity, that's to take a limit on that bound. And that part will go to 0, and then we simply plug in n, so we end up getting, and then subtracting that off, so we end up getting 1 over 2n squared. And we want to know how big this n should be so that we're less than 0.01. We can rearrange this inequality, or just plug in values of n until we get something less than 0.01. That would work too. Trial and error, but we can rearrange this. Let's just think of this the following way. So this is the same thing as 2n squared greater than or equal to 100. By taking reciprocals, it reverses the sign. So then we get n squared needs to be bigger than 50. That means that, in particular, n has to be bigger than or equal to 8. Because that's the integer that will actually get us there. 7 will be too small, but 8 and up will work. So that means that our ending number will be n is equal to 8. Now, when our ending number is n is equal to 8, we've actually added 6 terms up. We've added 3, 4, 5, 6, 7, 8, and you can check there's 6 things there. So we've added six terms of our series are enough to add here to ensure that we're within 0.01 of the actual sum. Thanks for watching.